finally made it. This is key number 4. Let's do it. All right. So we have to solve for x. So um, let's first take a look at what we got here. We got sine x, we got cosine x. We got a whole bunch of stuff going on here. So let's first realize we're trying to solve for x here. We have 4 sine x cosine x equals 2 sine of x. This is really messy. So I think I'm going to take the same strategy I've taken, I think, twice already. I'm going to do some substitution. So I'm going to call a sine of x, and then I'm going to call b cosine of x. And the reason I'm doing that is to try to simplify just what I'm looking at visually. And so like what I'm looking at is 4 times sine of x, which is just a, cosine of x, which is just times b, and this is equal to 2 sine of x, and sine of x is of course just a in this case, which makes this a whole lot easier. Like this doesn't look nearly as bad as it did a couple seconds ago. And so what I notice is I have everything multiplied, which is really important. But what I really see here is that I have an a on this side and a on that side. And so if I divide both sides by a, they are gone. And those are actually just canceled out. Because if I have a multiplied on both sides, if I divide them, those a's are going to cancel out. And so we end up here with a 4 times b equals 2. So if I divide both sides by 4, I end up with b equals a half, and that's really what I'm being asked to solve. And again, this is where the substitution method really starts to make sense, because it looked pretty crazy a second ago, but what I'm really solving is this b is 1/2. Now b is cosine, oops, I didn't mean to erase that. B is cosine of x, so now if I back substitute, rewrite b as cosine of x, so cosine of x equals a half. Now this is actually a really simple problem. I can go to my unit circle and find out where cosine is a half. Cosine is the x value, and so I immediately see a cosine of being a half here, but I also see its counterpart down there. Now I don't know how, I'm just going to assume I'm going to restrict this to just one rotation, but x now has 2 different values. One is going to be pi over 3, and the other one is going to be, what's that? 5 pi over 3. Or if you insist on using degrees, 60 degrees or 300 degrees, since I never really specified which in this problem to give. And I wrote all that off screen, but I was just recording the answer. There you go. All right, let's slide over. Oh goodness, we have fourth powers, we have second powers. How are we going to do this? Well, you know what trick I'm about to do. So I have these cosines. So the first thing I'm going to do is just replace it. So a is going to be cosine of x, right? So when I rewrite my problem, this is 4 times a to the 4th power minus 7 times a to the 2nd power plus 3. Now this looks like it still might be impossible because I have these 4th powers. But the essential observation to make is that this is a 4th power, that's a 2nd power. And so I can essentially treat this problem, over here, I can essentially treat this problem as like 4a squares minus 7a plus 3. And I think this would kind of work the same way. Yeah, plus 3. So what I'm going to try to do is actually make an attempt at factoring this first. Then if that doesn't work, then we'll maybe try like quadratic formula or something. But hopefully the factoring will work. Let's see. So, okay. Well, I know the last 2 numbers have to multiply to make 3. So I'm going to take a stab and say that's going to be 3 and 1. Because it's a prime number and that's the only thing it can be. My first 2 numbers have to multiply to make 4. Let's try 2 and 2. That makes 4. And of course that should be an A and an A. So let's just kind of test this out. So it's only the middle terms that are really going to kind of make this crazy on us. And so let's just see if I can make these numbers and multiply to make 7. And so if I take the middle terms, will be the result of multiplying 2a times 1, which is 2. And then the middle here would be 3 times 2, which would be 6. So 2a's and 2a's and 6a's, I can't make a 7. So That doesn't mean we're sunk. It just maybe we have to do some adjusting. Um, oops. So instead of 2a and a, like what if I use 4 and 1? Because that's another way I can make 4. So like what if I put a 4 here, 4a here, and I put a 1a here? That might work. Okay, so 4 times, let's get our coloring back. All right, so to get our middle, so like our first term still works because I have 4a times 1a. Our last term still works. I have 3 and 1. Now in the middle, I have 4. Okay, I have 4a times 1, which would be 4a. And I have 3 times 1, which would be 3a. Now I can make that as negative 7a. If I make that negative and that negative, these would be negative, and that would be my 7a. So yeah, I can totally factor this. So these are going to be my factors. 4a minus 3, 1a minus 1. Now, this would factor into 4a squared minus 7a plus 3. Um, but I was actually asked to factor with a fourth power. But again, if you notice, we have square power, 1 power. This is 2 and 4. And so if I just increase the power of a to 2, and increase this power of a to 2, that should account for my fourth power, and then the result should be adding a squares together, and then I'll get my a term in the middle. Okay? And so to solve this question, for a, I just have to figure out when either one of these parentheses are equal to 0, which means I need to know when 4a squares minus 3 is equal to 0. And then I also need to know when a squared minus 1 is equal to 0, which means I can just solve for a. So let's do that. Okay, so plus 3 here, plus 3 here. So 4a squares is equal to 3. Let's divide by 4. Okay. So we have a squared is equal to 3/4. And so, of course, last step, let's square root. And so we end up with a is equal to plus or minus square root of 3 over square root of 4 would be square root of 3 over 2. Okay, we'll revisit that in a second. Let's go over here and solve this one. This one's actually going to be a little faster. So here we have plus 1, here we get plus 1. And so we end up with a squared is equal to 1. So if we square root both sides, we end up with a is equal to plus or minus 1. Okay, so to recap really quick, we're trying to solve for x. X is wrapped up in cosine, so I substitute cosine in for a just to do the work on this problem. So once I had some factoring to do, even though I had a fourth power and a second power. Instead of just factoring with a's, I factor with a squares, and that'll create my fourth power. Not a big deal. And so we end up with these two numbers equal 0. And this is an algebra 1 thing. If you have two things in parentheses being multiplied equal to 0, I have to figure out what each one of them is equal to 0. So I have to solve a mini equation. I have to figure out where 4a squared minus 3 is equal to 0 and where a squared minus 1 is equal to 0, and I did that. Now, this is not the question. This just helps us understand how to get the question. And so if you recall, a is the same as cosine of x. So I did that substitution. And so what I'm really asked to solve here is when cosine of x is equal to either the positive square root of 3 over 2 or negative square root of 3 over 2. Or I'm asked to solve, and I'll resubstitute cosine for a, where cosine of x is equal to either positive 1 or negative 1. Now, this seems difficult. It's not, because these are direct values in our unit circle. And so if I want to know when the cosine value of x is either positive or negative square root of 3 over 2, I just have to find those. And so looks like it's going to be positive square root of 3 over 2 here. I'm just going to make a list here at pi over 6. Let's follow that around. No, no, no. It's negative right here at 5 pi over 6. Uh, Negative again here at 7 pi over 6. And let's see. Positive square root of 3 over 2 at 11 pi over 6. Okay. So once again, here's where substituting can actually simplify our problem a lot. If I go over to this side, I want to know where cosine is either positive or negative 1. Well, it's positive 1 here. It's a negative 1 there. So it's actually only a couple answers to this one. It's either going to be 0 or it's going to be pi. And I guess I can throw in 2 pi as well, because technically this is both 0 and 2 pi, right? So again, a complicated problem, but not an impossible one if you have a good grasp of what composite functions are all about. So a function within a function. So we simplified by first just getting cosine out of there so we can just solve the algebra part of it. We got it down to the point where we realized what the a values have to be. And now we reconsider a values to be cosine, find those values on the unit circle. And those, we have lots of answers here, but those answers are all based on the fact that you can actually get the algebra done. And that's really, again, been the theme so far this semester. It's going to be a theme all semester. It's all really about the algebra now. It's not complicated algebra, but you have to be really sharp at it. So let's, again, recall that this is no different than asking for f of g of x, like this, all right? And we're told all the information we need. So again, I think I'm going to approach this by first finding some values. So even though I'm asked to find f of g of x, the first thing I'm actually going to find is g of negative 10, because I'm told the x value. And so we have this, oh, here we have some crazy stuff here. We have 2 over 5. Instead of x, of course, we'll have 10 minus 10 times 10 minus 1. So let's play with simplification here. Let's not deal with a fraction yet, because 10 squared is actually going to be 100. Minus 10 times 10, which would be 100 minus 1, right? So we can do some quick simplifying here. We get 5 goes into 120 times. So this is going to be negative 2 times 20 minus 101, because negative 1 minus 100 is minus 101. Negative 2 times 20 is negative 40. Subtract 101. So this will be negative 141. All right. So if that's going to be the g value, we can now take that and substitute in the f function. And so we're really finding f of negative 141. The f function is given to us here. It's going to be 1/2 times negative 141, minus 4. So I can take this value of 141, stick it in for the x value for the f function. And so this is going to be 1/2 of negative 145. And so half of 145, she'll see, should be negative 72.5. Okay. So, oh man, another one of these. So you probably guess at this point we're going to use Pythagorean theorem, do a bunch of algebra, probably complete the square at the end. You could use quadratic form if you want, but I prefer completing the square. I think it's faster. Anyway, let's get to it. So we have a squared plus b squared is equal to c squared. A value is going to be x plus 2. B value is going to be x minus 8 squared up, and that's going to be equal to 4. So again, you can think of this a couple different ways. It's a squared value, so you can certainly expand it. And so x plus 2 times x plus 2. And then you can run like your double distribution, x times x, x times 2, 2 times x, 2 times 2. Either way, you'll end up with x squared plus 4x plus 4. Same thing with the x values. You'll end up with x squared minus 16x plus 64. And that's equal to 2 squared, which is still 4. Right? With some cleanup, we end up with 2x squares. We should have minus 12x, because negative 16 plus 4 is negative 12. And then 4 and 64 make 68. And that's, of course, going to be equal to 4. Again, we're going to solve this using completing the square, so let's do a couple things. Let's get this 68 over to the other side of the equation by subtracting 68. And so we end up with 2x squares minus 12x is equal to negative 64. which doesn't bode well for us, but let's see what happens. The other thing we should probably do is divide out at 2. Okay, and so we end up with x squares minus 6x is equal to negative 32. All right. Now let's go ahead and complete the square. So let's see, we have x squared minus 6x plus some unknown number is equal to negative 32. That unknown number, well, the squared binomial is going to be x minus 3. And so that unknown number is going to be 9, which I also have to add to the right-hand side. Let's see, 32 plus 9 would be 7, negative 23. Right? So plus 2 plus 7, so yeah, it'd be 23. So let's square root both sides. We end up squaring a negative, but that's not really arduous, because we know we'll just end up with the square root of 23 times I, plus or minus, of course. Last step, let's add the 3 over. And so x is going to be equal to 3 plus or minus square root of 23 times I. So we have an imaginary result, which is fine. It's just it's not one that it's going to make much sense in this problem. So you can also probably say that this has no real answer, so there's really no answer for x that makes sense. But the exercise is in the algebra, and that's what we really wanted to practice. Question 5. So we're back to factoring these polynomial expressions. So we have to make, again, some observations right up front. So if you look at this particular expression, we have an r in each term. So we can at least take that out of the expression before we try to factor it. The coefficients aren't going to follow such a nice pattern, so we'll leave those alone for now. So let's first take this r out and then build that multiplication problem behind it. If I take r times 9p squared, that'll give us our first term, then plus 73p, and then, of course, plus 70 at the end. So now we're left with this quadratic, which gives us confidence that we should be able to factor it. Again, it's one of those situations where we don't have our leading coefficient as just a 1, and so it might take a little bit of work to try to figure out the factors. And it might turn out not even be factorable, so we should also acknowledge that. But we should at least try to factor this. So let's give this a shot. So again, let's look at our first and last terms to try to inform what numbers we're going to use to do factoring. So we have 70 and we have 9. So 9 only comes in a couple different forms, 3 times 3 or 9 times 1. I'm just taking a guess here. Let's try 3p and 3p to make that 9p squared. For 70, let's try 7 and 10. And so before we proceed forward, let's just see if we can even try to get the 73 out of this. Remember, that comes from the multiplication of the inner and outer terms. So we multiply the inner terms together, we're going to get 21p. The outer terms, we're going to get 30p. Well, 30 and 21 make 51, not 73. So we know at least these are not the right combination of factors. And again, we should try to think also that this might not be factorable. So 3p and 3p, well, there's no variation in changing it. So maybe we just try another factor for 9. So let's try, I don't know, p here and 9p here. And so again, evaluating the inner and outer terms, 7 times 9 would give us 63. 1p times 10 would give us, or actually 63p. 1p times 10 would give us 10p. Well, look at that, 63p plus 10p would give 73p in the middle, so we did actually find our factors. And sometimes factoring isn't going to be like a formulaic type of thing. Sometimes it is going to be just a lot of guess and check and grunt work. So now let's adjust our signs. We need to make a positive 73p, so these should both be positive. And so that will end up being our final factored form. All right, let's take a look at 9x squared plus 7x minus 56. So again, it's a quadratic. It may not be factorable. We should at least take a shot at factoring it. And so again, let's think about numbers that multiply to our first and last terms. We're dealing with a 9x squared again, so let's try 3x and 3x. 56, let's see, 7, 8. Let's try 7 and 8 for those factors. I don't know if this is going to work, but we should take a shot at it. And so the inner terms would give us 21x. Outer terms would give us 24x, where we're trying to hit a 7, and so those are way too large. Even if I were to subtract one from the other, I'd still only have 3, and that's not 7x. So again, let's do some adjusting. Let's take the 3 and 3. Let's try to make this 9x and 1x. Again, checking our terms, that will give us 7x for the middle, 72, excuse me, for the outside terms. And again, even adding or subtracting those terms, we're not going to get that 7x. And so for this one, at the very least, at this point, we can reasonably conclude this is not factorable. So just because you're set to try to factor something doesn't mean it's going to work, which is why we end up having all those quadratic solving strategies. Factoring is nice if you can do it quickly, but if you can't do it, there's always something to fall back on. In this particular case, we're not solving, we're just trying to factor, and so we can stop here and make the claim that it's not factorable. All right, simplify the polynomials. So if you've been doing all the homework up to this point, you know what we're probably going to do first is to do a little factoring first, and hopefully we can get some factors to cancel. Again, make an observation that every term, at least in the top part of that expression, has at least an x, and so we can rip that x out of every term. If we do that, we end up with 4x squared plus 43x plus 30. And then on the bottom term, we can probably do a very similar thing because we have 32 and 24. And so that tells me we can take an 8 out of every term, and that'll leave a 4x plus a 3. So at this point, it doesn't look like anything's going to factor, but do acknowledge that the top is a quadratic. So we could try to factor that quadratic, but in this particular case, since we have a division problem, we can also check the bottom factor against the top expression to see if it is a factor. It is a division problem, so we can go back to polynomial division. So we're just going to check here if 4x plus 3 is a divisor of 4x squared plus 43x plus 30. Now, if it turns out that this does divide into it evenly, it has to be a factor because that's what factors do. So, for example, if I take a number like 24 and I'm wondering if 3 is a factor, I can take 24 divided by 3, and if I end up with an even number, or I'm sorry, a whole number, like 8, no decimals, that means 3 and 8 are factors of 24 because if I could divide 24 by one of them, I get the other, which means I can multiply those two numbers together to get 24. And so it should work for polynomials too. So I don't know if it's going to work, but we can just give it a try. If I have 4x squared as my target, if I multiply by x, that'll be 4x squared. 3 times x is, of course, going to be plus 3x. Now I subtract that from my original polynomial. I'm left with 40x plus 30. Now we can continue with the next step. So I want 4x to go into 40x. We'll take 10 of those to do it. And that'll leave me with 30. Now if you look here, when I subtract the second line, I end up with 0. And so that means 4x plus 3 is a factor of the top quadratic. And that means the top quadratic would factor into 4x plus 3 and then x plus 10. And the bottom, of course, will be 8 and then 4x plus 3. The good news here is that we have some terms that will cancel, so we can get rid of those. Remultiplying the top, I end up with x squared plus 10 all over 8, and that will be a simplest form. So we saw factoring kind of in different variants in the other assignments. So we have some factoring where it's going to be a little tough to factor, just because those coefficient terms aren't as nice as we expect. We have a case where you can't factor, and then over here with the rational expression, where we can use what you know about division to see if a factor is going to work or not. ACT prep, please note on your sheets, if you didn't get one that was corrected, that should be an 8y, and that'll totally mess you up on this problem if you don't make that change. So this is, again, one of those classic ACT problems. It's really an Algebra 1 problem with some twist to it. So you have to have some knowledge of what systems will do, particularly if you want no solution. So there's two ways to look at it. One is if you solve this using like elimination or some kind of substitution, some algebraic method, and you end up with some crazy answer like 10 equals 3, an equation that cannot be true. That points to the fact that you have no solutions to the equation. You can also think of this graphically, which is how I tend to think about these things. If solutions are where they intersect, that means these lines are actually need to be parallel. And so really this question, the way I'm going to approach it is, what's the values of B and C that make the lines parallel? So please recall parallel actually means two things. One is that you're going to have the same slope for both lines, and two, that you had to have different y-intercepts. So that's what we're going to have to figure out. This question is really asking me, for what values of B and C will you have the same slope but different y-intercepts? So the first thing we need to do is take this first equation and figure out what those two values are. In standard form, it's not easy to extract. It's not impossible. It's just not as easy as like y equals mx plus b form. So that's the first thing I'm going to do. I'm going to solve this guy for y so I can get the right information. And so we'll see, we'll have 8y is equal to negative 2x plus 2. And then we'll divide both sides, or everything, excuse me, by 8. And that should reveal the information we need. So we'll have negative 1 over 4th x plus 1 over 4. And so in this particular case, negative 1 over 4 would be my slope. And then 1/4 will be my y-intercept. And so what I really need to do is pick values for b and c that end up having the same slope but not 1/4 as an intercept. So let's grab the second equation. So we have x plus by equals c. What I think I'm going to do is solve this guy for y as well. And so we'll subtract x on both sides. By is equal to negative x plus c. Divide everything by b. And so we'll end with y is equal to negative 1 over b, x plus c over b. Now again, we want this 1 over b to be the same thing as negative 1/4, which tells me right away that b has to be 4. So we're down to two choices. It's got to be a or it's got to be b, because those are the only ones that offer the correct b value. And so now we need to pick the right c. And so if my choice is a, that makes c over b 1 over 4, which is precisely what I said we couldn't have, because if they had the same y-intercept, so they're the same line, and if they have the same line, it has infinite solutions. And so my value has to be c, because that would make it 3 over 4, which is okay because it's not the same y-intercept. So again, just like I said, I've been saying a lot, this theme for this semester is really a bunch of Algebra 1 with pre-calculus as a conceptual base. And so that's all you're seeing here. This is really an Algebra 1 problem, but you have to be thinking at pretty high level to solve it. Last one, let's see, we have this equation, 3m minus 4 to be equal to 6n minus 8. And I want to know which of the expressions is equal to 3m minus 8. Well, if you look on the left-hand side of the equation, we're pretty darn close to 3m minus 8. And it wouldn't take a lot to change it to 3m minus 8. All we really have to do is to subtract 4 from that side of the equation. But all the way back from who knows when, if you change one side into an equivalency, you have to change the other the same way. So if I subtract 4 from the left, I got to subtract 4 from the right. And so if I want to build 3m minus 8, the result will be 6n minus 12. And so that would make b our answer. So if I change the 3m minus 4 to the expression we need, it would change 3n minus 8, or excuse me, 6n minus 8 to 6n minus 12. All right. So guys, that's all the homework. So remember, you have a test coming up on Friday. It's based completely on the homework, which also has to do a lot with what we've been doing in class up to this point. So all this is a great thing to study. And remember, to take that test on Friday, you have to show me all the work completed. Okay, so be prepared to do that, please. That's it. Thank you.